Class 3, question 6. We did question 5. We'll do question 6 now. Let's read it. Using the regression results in column 3, do there appear to be important regional differences? Take a look at column 3. It's, if you do not have the question paper, it's on the screen. Question 3, sorry, column 3. Now the question is about this. About these dummy variables. So it's still, I think I should adjust my position. Still getting the lines curvy. So yeah. So this is about this 3 variables jointly. Are they important for this model? In other words, what do you think? What should we do to check if these 3 variables are jointly significant? So we need to do joint significance test, right? You do significance test using t-test, t-stats, yeah? And you compare it with t-critical from the table. So what should we do with f-test here? Because joint significance is tested using f-test, right? We should calculate f-stat using the f formula, f-stat formula, and then use this f-stat as a number, right? Single number, a single or multiple digit, and use that to compare with a critical value from the F table. Now, if you read the table, or you have read the table, here is F-stat. F-stat is given to us. For this model, with 3 restrictions, you have F-stat 6.10. So you know where I got this from. It's from this. It's given already in the table. And notice it says F statistic for regional effects being equal to 0. So null hypothesis for this F is this. Any statistic should be based on a hypothesis, right? Any statistic that you calculate. So this would be beta. Which beta is this? Northeast is beta 4 equals beta 5 equals beta 6 and equals 0. This is a null hypothesis we have. Beta 4, 5, 6, this is 6, equals, an alternative is that not null. In other words, they are not equal to 0 jointly. You could write it separately, like beta 4 equals 0, comma, beta 5 equal to 0, comma, beta 6 equals to 0. This is fine as well. And we got this, we are given this actually, we don't have to calculate. Now, this has to be compared with critical value before make a decision whether to reject this null hypothesis or not. Now, what are the degrees of freedom for F? There are 2, degrees of freedom 1, degrees of freedom 2. Degrees of freedom 1 is the restrictions, number of restrictions. We have 3 of them. In other words, 3 betas being equal to 0 jointly. So that's 3. And the degrees of freedom 2 is usually large, it's the number of observations minus the number of regressors minus 1. And in this case, we have how many observations in the model? 120. Oh, 420. I think that's from previous, isn't it? Class exercise. This one is slightly different though. Do you remember? Look at the first page. It's on the first page. Do you have the printed thing? Yeah, it's on the first page. N equal to 4000, isn't it? Scroll up to the first page. So you're looking at the class 2, I think. So N is equal to 4000, so that's a large number. Instead of writing 4000, we put in infinity sign, and that is equal to, and if you have the F table, this would be equal to 3.78. Yeah, this is very large, yeah. I think F test only gives you up to 500. F table.
Because variable be right?
Yeah, no, a bit high. Go maybe 100. Yeah, maybe something else. But if you look at the F table, I think some F tables have only up to 120. Yeah, but usually in test you get infinity anyway. So in the test, when you do Don't forget to put infinity, unless it says a small number, n is equal to small number, less than 100, let's say. Then you have to put that number here, because then the critical values differ, yeah, for small values than large. I mean, large value more or less the same. A value for 4,000 observations and value for 5,000 observations, they're more or less the same critical values. Now, as usual, there's a rule of thumb. You have to compare f stat with f critical, and in this case, f stat is greater than f critical. What is the decision? Reject or accept null. If your f stat is greater than f critical, what is the decision? Like a t stat being greater than t critical, yeah. Reject, exactly. Just it's the same way as in the t. Yeah, in the t-test we reject null if t stat was greater. So do the same here. Reject null. Null hypothesis. Now, what is the economic meaning of this decision? What do we conclude? What do we comment in a sentence or two?
They're significant.
Yeah, they're significant jointly. So they need to be there, isn't it? So we retain these variables in the model. We keep them in the model. They are jointly significant. So there are significant differences in wages across regions. Yeah? We have 4 regions here. One of them is omitted, that is West. However, South wasn't significant, was it? Do you remember we did starring? We put stars on this. Last week we put stars. We had double star here, and double star here, but no star on this. This was not significant. You can think that we should drop it, but it appears actually they're jointly significant, so keep them. You could actually replace the South with West and see, who knows what you get. I think most likely this would be again something non-significant, but you have to test it. So we'll keep them. So regional differences are important. The determinants of average hourly earnings, that's the conclusion. Yeah, regional differences are important determinants of average hourly. So regions, sorry, no, I should say regions are important determinants of average hourly earnings. Okay, next one. B. Next one is B. Does anyone want to comment on B? B says, why is the regressor West omitted from the regression? What would happen if it was included? What do you think? Alright, so let's do it together then. Let's go back to basics, guys. I think if I show you the basic, you'll say, oh yes. So let's do that. Yi beta 0 plus beta 1 x1 I plus beta k x k I plus ui. Now, this is generic model, right? Now, these are variables. There are k variables in this model, and then each variable will have a coefficient estimate for each of them. Yeah. Then, where is the variable for beta 0? If each variable should have if each estimate should have a variable, where is this one? Intercept. So it is intercept, right? So what is it?
West.
No. Think about it. It's usually 1, and we call this one x0 I. And it's usually x0 is usually 1, 1, 1 for each I. But x1 could be different, you know. Yeah, could be different. So we need x1I there with an I. But with x0, for each person, it's 1, 1, 1, 1. Now assume that we have three dummies. So basically three categorical variables, which are x2, 0, 1, 1, 0, 0, 0, so on and so forth. x3, 1, 0, 1, 0, 0. x4, 0, 0, 0, 0, 1. Yeah. Note each observation here, observation number 1, person number 2, person number 3, person number 4, person number 5. Yeah, there are 5 people surveyed. These are their wages, let's say, per hour. Now these are regions they are coming from. This person is from x2 and number 4 is from the... So basically x2 takes 0, otherwise 1, 1, otherwise 0, right? Now, if I sum this up, it will be 1. If I sum this category up, 1. If I sum, so I should get 1 for each 1 here, right? If I sum all this across variables, 1, right? So that's what you will see if you include, this is all 3 dummies. Include all 3 dummies, you get 1, 1, 1. The sum of them will be 1 across variables. And at the same time, my intercept is 1, 1, 1, 1. It tells me that x0 is actually a perfect linear function of x2, x3, and x4. What is the result if I include all of them? Perfect multicollinearity. And this is called dummy variable trap. To avoid this, I need to drop one of these 3. We can't drop intercept. It needs to be there, especially in the wage equation.
How did you get? Can you repeat it again?
I just assigned randomly. And notice that if x2 takes 0, for the first person, x3 or x4 should be 1, either of them.
Yeah.
So there's 1 here at least. So this person is from, let's say, region x3, region 3. And this person says they are from region 2. Ah, by the way, let me do this. I have a better example. Let's look at this. It takes time though. So we have person number 1, forget about intercept for now, has a college degree, is female or male, because 0, is from northeast, not from northwest, not from south, not from west. Person number 2 doesn't have a college degree, is male, from northeast, so on and so forth. Now, person number 5 has a college degree, is female, is from Midwest, and 0. So you see, each person will be from one of these regions, right? And I have 4 regions here. Now, if I do this, if I run this regression now as it is, usually I drop the intercept because eViews creates the intercept automatically. If I run this regression, eViews doesn't allow me to do the inference. It just gives me an error message, says stop there. That's because intercept, which is this one, is a perfect linear function of the sum of these. So if I do this sum across these dummies, you will see that it's 1, 1, 1, 1 across dummies. So in each case you have total being equal to sum. And when a regressor is a linear function of another regressor, you have a multicollinearity, perfect multicollinearity. Is that clear? You have a perfect multicollinearity. Because, yeah, sum of all the dummies equal to 1, and I have exactly the same thing as an intercept. It's basically like you have 2 variables, but they are the same. If you enter them into regression, you get an error.
Well, which function in this case is a function of what?
So intercept is being a function of the sum of this. So I need to drop this when I run regression, and then you see what I have. At least they are the 0 zeros. So they are not perfect function. This intercept is not perfect function of all 3. I'll put it back now. I can demonstrate this. Let me demonstrate this. But this will take time as usual. So I'll delete this. Delete this now. Right. I have now northeast, northwest, south, west. Let's put 0 here. I won't include it basically. Could be there actually. Let me put it first. I'll show you the case with multicollinearity, which is dummy variable trap. A case without west. Data. Where is my thing? Data analysis. For some reason, my data analysis is hidden here. Yeah, I don't have the data analysis in this for some reason. Right. If you run this regression in eViews, you will get this bump noise. Let me save it. Okay, I saved it, don't I? Why is it not starting? Okay, it's taking time. Right, so if I go to open a foreign data file, and I need to just find it. Where did I save it? Right. Now let's run this regression using some variable there. Let's take college as the dependent, female, Midwest, Northeast, South, and West equation. So you see, I included all the dummy variables, all the regions, 4 regions. You see, near singular matrix error. This is called perfect multicollinearity. So perfect collinearity. Okay. Now let's drop West. Just in the case of your example, West is dropped. Now I have the equation. You see, you shouldn't include all the dummy variables, categorical variables in the equation. It is clear now.
What's the limit in terms of that number of variables?
You can have as many variables as possible as long as you have degrees of freedom for t-test. However, with the categorical variable, you should drop at least one of them.
So just drop one.
Drop one, yeah. You can drop any, but one. Don't put all the dummy variables if you have them, because the C will then be a function of them.
So the West is our dummy variable.
No. West is omitted one. Omitted dummy.
One West.
Yeah, only one. I just removed West. And Midwest, Northeast, South are also dummy variables. And female is also dummy. But if I include all the dummies in the category of regions, it will be exactly one. Some of them. It's regional dummies here. One of them is being omitted. But you can have as many dummy variables as possible. It's just from within one category, let's say regions maybe, you shouldn't include all this. Or if you have, degrees, college degree, high school degree, master's and PhD. If you have such a categorical variable, drop one of them. And then include only 3 of them. High school, BA, and master's. Drop PhD.
So why do you have to drop one dummy variable?
Because of this example that I showed. This is an error. Multicollinearity problem.
So we want to show
There is no, so you shouldn't have error. If you have error, you can't really run the regression.
So in this case, you got categories of all regions. South,
Yeah, I have the categories of regions here now. And then last one is West. I'm only dropping that one.
If you drop South,
You have to put West back.
so you only drop one.
You drop only one.
Why? Because you got degrees of freedom.
No, it's because of multicollinearity again. Let me show you again. I add the West again. You see, these are all regions now included. I cannot run the regression. Okay? And I'll go and drop now this time South. Now I should be able to run. Yeah, I have now
So where's the conflict?
West now. The conflict was error. It doesn't show you what conflict. I showed you.
So 0, 0, 1, 0, 0, 1, the same as this one, which is both like linear function of your constant.
Now with this setting, you won't have a linear correlation or linear function. Sorry, not correlation. You know, here, if you sum this up, you used to get ones. But if I just drop west and then sum them up again, notice what happens. This last 4 is 0 now. And my intercept was only 1, 1, 1, 1. And now intercept is not a function of dummies anymore. Because, you know, it is 1, 1, 1, 1, while your dummies, added dummies doesn't add up to 1. It will have 0. So this will allow you to avoid this problem. To go in and then run the regression. And notice that these dummies are control variables, really. I mean, they are not your main. Your main variable is this female, and you want to make an inference on this.
So if you go, for example, 5 regressors, you drop 1.
Yeah, if from the same category, 5 regressors. Let's say you just drop 1 and run the regression.
And if you do 5, it will be an error of multi-correlation.
Yeah, you get an error, just like I showed you. Yeah, exactly the same error in every software you get. I think if you're doing Stata, I think it will not have an error. It just drops one of the dummies automatically for you.
Do we assume heteroscedasticity?
No, you have to assume homoscedasticity. Yeah, you have to. There is always heteroscedasticity. These in the errors, so you have to just tick the robust standard errors option. Yeah, always. But only in mechanical applications, not in the theory. Just if it asks, just mention this. And it took us a while, didn't it? Yeah, we lost half an hour on this. Okay, I'll be quick now in the next remaining because we need to be moving into the next. This would be on the YouTube channel, so you'll be able to watch it later. If you didn't understand now, I'll have to just move on, guys, because we have a class 4 as well to do. And I have office hours 10 to 12 on Friday.
What room?
Sorry?
What room?
What room?
Number.
Okay. Does it not have my room number on this? You joking? CB203A. I didn't realize. Didn't I put my number in? And you didn't. Sorry. CB203A. CB203A. It's central building. It's near the IT help desk. If you have been there. Yeah, you probably has it there. What is it on the?
I think we got lectures.
Yeah, it's basically on somewhere there. So. Okay, let's do the next one. Construct a confidence interval. 95 confidence interval for the earnings differences between Juanita and Molly. So it's an expected earnings difference. Now, Juanita is from the south. And Molly is from... Where is Molly from? Are you reading?
Yes.
West. And west was omitted variable, right? It's dropped. Now, this, when you interpret this dummy coefficient estimates, it's relative to the omitted variable, omitted category, sorry. So a person coming from northeast will earn 69 cents per hour more than a person from the west, from the omitted variable, omitted category. A person coming from Midwest will have 60 pence or 60 cents per hour more earnings than a person from the West. And a person from the South will have 27 cents less wages per hour than a person from the West. You see, it's all relative to West.
But where is your West?
West is omitted. So basically, Juanita earns 27 cents per hour than a person from the West. And in this case, it's Jennifer, isn't it? Oh, Molly, sorry. So Juanita earns 27 cents less than Molly. If you read, Molly is from West. If you read the question. Now, given that, we need to construct a confidence interval for them. And here it's beta 6 hat, right? Because south is x6. Plus minus 1.96 again, for a reason, yeah? So plug in the number from the table, and standard error of estimate is 0.26. And what can you see here? One band is on below 0, one band is above 0, right? So 0 should be in there then. So there's a 95% probability of 0 being in that band. Effect is 0, so it's not significant, right? And remember, we had no stars as well here. That's why 0 is in the 95% confidence interval band. Confidence band, sorry, not interval band. Same thing. Right, that's that. Next one. What's the expected difference in the earnings of, who is this? Calculate the expected difference in earnings between Juanita and Jennifer now. And if you know, Juanita was from South, Jennifer was from Midwest, and we have the coefficient estimate for them. So it shouldn't be a problem to calculate. That is minus 0.27, and we're looking at the difference. So this is Juanita's wage per hour, which is this thing here, relative to Jennifer, sorry, Molly's. And we're looking at Jennifer, who is from Midwest, right? This one here, 0.6. This is the earnings difference, expected earnings difference between the wages of Juanita, earnings difference between Juanita and Jennifer, basically. Now another question, so I'll be quick in this case. Explain how you would construct a 95% confidence interval for the difference in expected earnings between Juanita and Jennifer. Juanita and Jennifer. Now this won't be possible because this is the difference, right, between their earnings. But this is not a single coefficient. It's two coefficients. There are two coefficients. These two coefficients.
How did you do the first case?
Hmm?
How did you do the first case?
This one was between Molly and Juanita. So we had one coefficient there.
Were they both from the same region?
No, Juanita was from South and Molly from the West. So West was omitted, isn't it? Now, in this case, both of them are not omitted. So we need to get one of them omitted. Then it will be possible to do. Because we need a standard error for that coefficient. And it will be possible if we just drop Midwest. If we drop Midwest and add back West and run the regression, Juanita's coefficient estimate will be this. And it will have coefficient standard error in the bracket as well. Then we can use this coefficient estimate and standard error to construct a 95% confidence interval for these two guys, earnings differences. Yeah. So for confidence intervals, you need standard error of regression always. Although we have the differences, we don't have the estimated difference. We have them, but we don't have the standard error for this coefficient estimate. We don't have it. So we need to drop Midwest, who is Jennifer in this case, and add back Molly's West, and run the regression for the South. Then you get this sort of thing, this number. And then you will be able to construct 95% confidence interval. Done. Next one. I'll not ask if you understand or not because we need to move quickly. Evaluate the following statement. In all of the regressions, the coefficient on female is negative, large, and statistically significant. This provides strong statistical evidence of gender discrimination in the US labor market. Is this statement true? What do you think? We have the hypothesis already. Look, we have, that's a good question. You have the differences already with t-values showing us these are statistically significant. We had 2 stars for all of them. So these are significant values, aren't they? And also 2.64 difference. So basically, a female earns $2.63 on average here, that if you take that, or maybe 62 cents per hour, less than a male. Yeah, it's a negative value, right? And if you take it as a 40-hour week in the US, this would be $85 per week. And if you times it by number of weeks in a week, that working weeks, 50 let's say, you get about 4,000, right? And a half. 4,500 dollar difference between male and female wages in America. Is this true? Possibly true, but possibly not true. The possibly not true is the correct answer, because this is only from a sample of 4,000 people. Also, we didn't include many factors. We didn't control for factors. Could possibly absorb much of the effect on the female variable coefficient estimate. We could include religious differences. We could include background information. We could include race of person's race. We could include date of birth and period they're born, or conditions, economic conditions, and macroeconomic variables. They will certainly give us a different female coefficient estimate. So that's the answer. We need to control for more variables, and maybe then our coefficient estimate will be insignificant, or maybe it will be still significant. At the moment, we cannot say this is the final answer. We cannot conclude that there is a gender difference or wage gap. Okay, good. Reason is that there is not many control variables in the model. So apart from this regional differences and college degree, we don't have much. Yeah, age as well. We could include race, religion, other factors that could effectively make this non-statistically significant. So we're looking at the gender gap, remember? Okay. What was your question? There is none. What I am saying is, because we didn't have, there may not be, sorry, not there is, I should say there may not be gender gap because of omitted variables. We still have many factors to control for. The best way would be to collect information on the population rather than samples. Then you can say for sure. Because this is sample of 4,000 out of 200 million working people. Isn't it? It's very tiny amount. In America, I think you have about 200 million working population. So, and also I think this has an age bracket as well. So it's about 100 million will be something in between 25 to 34, let's say. Then you have a huge population numbers that to look at. This sample will be peanuts, isn't it? Okay, let's start the next one. This is class 4 now. Class 4. Class 4. So open your class 4, download it if you don't have it. I'll just do this one quickly. It says sales in company are okay, 198 million. So calculate percentage increase in sales using the usual formula, okay, and compare this value to the approximation, log approximation. So let's calculate the growth rate of the sales. In that case, it will be you get something like this. And do the log approximation using natural log. Either one, because there's not much difference. So log approximation is good when you have differences between the observed values small. You know, if the observed value difference from 2 points, if they are small, log approximation is good for growth calculation. So if you're looking at the growth rates of GDP, that's fine. In economics, GDP doesn't fluctuate. You know, you can't get a country twice as rich as it was last year, right? They don't produce 10 billion tomorrow if they produce 5 billion yesterday, let's say GDP wise, gross domestic product. The same with inflation. Well, except for in Zimbabwe, overnight the inflation rate was 4,000%, isn't it? Crazy things. But in that case, don't do log approximation. This is not advisable. I'll show you. Look at the B now. B says, let's take 500. No, 250 would be enough, I think. Let's do 250. So 250 minus 196 over 196. sorry, timers. You see, this is not the same. A bit close, isn't it? Here I would say more or less the same growth rates, but in this case, log approximation to growth is poor. So you should go back and use the usual.
So use logs when
Differences are small. Time series in economics are usually not from observation to observation. They do not differ much. So log approximation is fine for that.
so for time series, use logs for time series.
Log is usually for time series, yeah. When you look at growth rates, but not cross-sectional. If you want to calculate growth rates from one section to from one observation to the other, usually you don't, but that won't be possible because cross-section could contain rich and poor countries. And if you increase it to 500, it's even worse. You see, 500 minus 196 is a huge difference. This is about something like 5. So this is the thing. And if you do log approximation to growth, very, very poor approximation, very bad approximation. So don't do log approximation when the observations too far away from each other. So go with the traditional, I mean usual, it's not traditional. Go with the usual approximation for growth, usual calculation of growth. No, it's not approximation. The first one is actual approximation, actual growth rate calculation formula. This ln is an approximation. This is a poor approximation in large differences. Okay, let's go to the next one now. To A. Says we have a model here. Now we need to do a t-test on this hypothesis. I think, can you think of this?
Why do you need to transform it?
Sorry, say it again.
Why do you need to transform it?
Usually we tend to have, I mean, with the t-test, this is a hypothesis you do, isn't it? But we have two coefficient estimates, and we want to see if they are equal. Yeah. Here, with the t-test, you can only look at one coefficient at a time. It's not two like this here. So we need to do something so that this thing becomes one single coefficient. In other words, let me show you what I want to say. This becomes clear now. Can we write this, for example? Exactly. So b1 minus b2 equals 0. Can we do that? Yes, because that goes to this side and with a negative sign, right? So subtract beta 2 from both sides, you get this. And I think if we think of this as one coefficient, then we can use t-test. But then where is the gamma coefficient? We need to make up one for us. Let's transform this regression model so that there is gamma. So I have beta 1, and I need to add something and subtract the same thing to bring my beta 2 into the equation. So this would be beta 2 x1i. Notice this is x1i with the beta 2 minus beta 2 x1i. Notice that it is the same thing. It's just subtracted and added. Plus my beta 2 x2 I. All I did was this part. I added this part and subtract, so this thing will cancel out automatically anyway. This thing cancels out. But then keep it for now because we need this.
You add and subtract.
Yeah. And notice what we do now. We just put this into one bracket. Sorry, this is minus here. I meant this is minus, this is plus. Yeah, we add and subtract to get this sort of thing. Now let's work further with this. I know common factor here, x1i for both of them. So factor it out of bracket. I get x1i plus. Now here, beta 2 is common factor here outside the bracket, right? So factor it out. Then you get x1i plus x2i. Oh. Now, one variable, one coefficient here. This is basically gamma, or phi or psi or anything you want. And these are observed variables. I can sum them up across i's, and I could be getting wi, let's say. You can put it, name it anything you want. But your solution comes with w, so I kept the solution notation. You can put z here if you want. So yi now will be beta 0 plus this gamma x1i plus beta 2 wi plus ui. That's it. Now, because we wanted to do t-test.
What's the difference between this one and the original equation?
That's a good question. What's the difference? The only difference here is the w. I have x1i here, which is the same. I just summed up the x1i and x2i as one variable. I summed them. I took the sum of these two, and they become one variable, which is wi. And this gives me this sort of coefficient estimate. Next week you will see how it's done. Yeah, but the only thing here we really did in practice, in theory we did a lot of calculations, this is the transformation. But in practice it's only the case of summing the two variables up and running the regression. You get transformed betas as a gamma. In practice it's a very simple thing. But in theory, it just requires the transformation manually. Then we are actually testing now this. And you know that gamma hat is actually the difference between beta 1 and beta 2. So we managed to test this hypothesis. It's the same thing as this, isn't it, this thing? So now we have single coefficient restriction, not two coefficients. Using this. So running this regression is for this one. It's from eViews usually. Yeah, you put this into model and you'll see that is a possibility to do. Next week I'll show you. I think the first question is about that. Class 4 or 5, yeah, class 4 is the first question about transform it so that you get this. And we do it in practice and you will realize how easy it is. Okay. Number 2b. What does it say? Maybe you do it. It's the same thing, by the way. All we need is a new statement of, let's state this, new variable here. Now we need to transform this model into a new one such that we'll be able to test this hypothesis. Again, there are two coefficients. We can't use t-test. So this needs to be some other coefficient estimate. Let's say gamma again. You can put any letter if you want. And in that case, the same principle applies here. Add and subtract something so that you have this transformed regression. So I will add alpha beta 2 x1i and I'll subtract the same thing. My usual x2i. Done. You see, I just added and subtracted this.
Can we just add anything in?
So long as you can get this, yes.
But do we have to add in B1 as well?
Beta 1, no, you already have the beta 1. So
So it needs alpha B.
all we need is this one here. And this needs to be positive sign here, it's a plus sign, so that this together can be one coefficient estimate when you take out the, sorry, factor out x1i. You see, I just added this part because they could be 0 together. But then I put the bracket between these two so that I have something different. So let me show you. Now new model will be now, if you factor out the beta x1i, yeah, you see this is a new beta now. It's a gamma now. And here we need to have positive sign, so beta 2 is common for both. Done. And call this gamma, call this wi, nothing changes. My x1i is still there, it just has a different estimate because of this transformation. Alpha is a constant, it doesn't have I, so
The overall result hasn't changed.
nope. We just managed to test this hypothesis that beta 1 plus gamma, sorry, alpha beta 2 is equal to 0. That's all we want to test. And we need this transformation. And in practice, we would only do this part here. We would create a wi by summing this or subtracting x1 times alpha from x2, and that will be new variable, and you run the regression, you get this gamma, and the test regression, this would be akin to saying gamma equal to 0. This whole thing would be akin single coefficient testing. But in fact, this gamma would be the sum of beta 1 plus beta 1 and alpha beta 2. Any question? Next 4 minutes. Can you fill in the form, please, the evaluation form? And I will ask for a volunteer to take it to the other building if you do not have a class. Anyone? Anyone going to Queens?